Thank you, and welcome everyone to the webinar today. This is part of our, as most of you may know, our small drinking water systems monthly webinar series. We did have a huge response to this webinar. Unfortunately, we are not able to allow everyone to join today, but in case you know some people who weren't able to join, we are recording this webinar and we will post it to our website for viewing at a later time. So before we get started, of course, today is the webinars on treatment technologies for removing chemicals of concern. And before we get started, I just have a couple things to talk about. First, if you need support, if you can't hear, if you can't see the slides, we do have a questions box there in your navigation bar. So feel free at any time to ask questions there related either to the presentations or to any difficulties that you're having with the webinar. Also, in case you didn't get the email, we do have the slides as a handout. There is a handout drop down there in your navigation bar, so you can keep a copy of the presentations today. And like I mentioned before, the questions box, asking a question at any point, we are going to have a Q&A session at the end of both presentations, so you can ask questions throughout the webinar, and we'll try to get to as many of those as possible at the end of the presentation. Okay, so we do give out certificates for attending this webinar. We do have a change that we need to announce for this month, starting this month. Although we are working on going back to, we typically give out continuing education contact hour. We are not going to be able to do that. We still will give out certificates of attendance. So if the requirements are the same, you can see here 1 through 4, you have to attend the live webinar for 60 minutes. And if you have people in the room with you who would like a certificate who are not logged in, you can type their name in the questions box for us. We'll make sure they get those as well. Or you can email webcast there number 3. We apologize, we can't give continuing education credit this time. However, certificates of attendance still are from EPA, will still show that you attended for 1 hour training. So hopefully those will still work for the majority of you. And we are beta testing this time to help with these certificates. We'll be doing poll questions after each presentation. So if you are looking for these certificates, it would benefit you to watch the webinar and try your best to answer the questions at the end of each talk. And again, certificates are only provided for viewing the live webinar, not recording. Okay, before we get started, just a couple of announcements, upcoming webinars. We have one on March 7th on lead service line identification and replacement. And this is the first in a new series, a quarterly series on case studies. And this is being held, our Office of Water at EPA hosts this webinar series. And then, of course, for this webinar series, we have one March 26th on lead management in homes and buildings. Registration will be available soon, but the information is on the website. And part of this webinar, we will be presenting on a new tool for identifying point-of-use filters certified to reduce lead. And you can see here the document is now available, so if you want to get that in advance, the link is right there on the slide. Okay, and with that, just our disclaimer about our presentations being reviewed. And we'll go ahead and move on to our first presenter. So this talk is on treatment for contaminants of emerging concern, including PFAS, cyanotoxins, and perchlorate. And with the emphasis, of course, being on cost-effective solutions for small systems. This will be presentation is by Tom Speth. And Tom is a professional engineer with EPA's Office of Research and Development and has worked in the field of treatment research at EPA for over 30 years. So Tom, we go ahead and get started.
Okay, great. Thank you very much, Michelle, and good to be back. And so it's good to see so many people interested in this topic, and we are working on increasing the number of people that our upper limit is. So hopefully in the future, we won't have that problem again. But it's good to see that there's so much interest in this topic. So I'm going to be overviewing very quickly three different contaminants of concern. Perchlorate, but I'm also going to be including nitrate into that discussion because it's a good story. And there'll be three technologies evaluated for those contaminants. Microsistence is the second area or second host class of contaminants that I'll be discussing, and then PFAS, per and polyfluoroalkyl substances, and covering three technologies for those groups of compounds. So a little plug. All of this information for these contaminants are included in the EPA's Drinking Water Treatability Database. It contains data that's in the literature for treatment for over 65 compounds, and includes nitrate, perchlorate, microsistence, and a class of different PFAS. And the link is shown there on the bottom left there, if you're interested. This is the opening page of the treatability database. You can click a contaminant, you can find a contaminant, you can find a treatment process, and then you can get at it either via the contaminant or the treatment process. If you choose a contaminant like PFOA, you see the listing of treatment processes for which there is information in the literature. Click on one of those and it will show you, for instance, granular activated carbon data for PFOA in this case. Okay, a little bit about EPA's cost models that I'll also be covering. So there are a number of different cost models that EPA has put together. We do this, the Office of Water is the lead on this, and they do these for setting national regulations, but also they have other uses, as you'll see today. And the ones in blue or bold are the ones we'll be covering today. So we will be covering anion exchange, biological treatment, GAC, and point of use, point of entry processes. And the links are down there below if you're looking at those different technologies and cost models. So okay, so right into why nitrate and perchlorate together. So well, there are two very important contaminants. Nitrate is a number of utilities exceed the MCL for nitrate, particularly small systems. And so it's nice to include that in this discussion. And for perchlorate, there's new state regulations for perchlorate, and of course the US EPA it's under regulatory consideration at this time. Both of these contaminants are fully oxidized, so oxidation processes, including aerobic biological treatment, won't work on them. And it kind of limits the technologies to technologies that are pretty much the same for these two contaminants: anion exchange resins, high pressure membranes, reverse osmosis or nanofiltration membranes, and anaerobic biological treatment, which is a novel technology in the drinking water field in the United States. And so I wanted to cover that today. So we'll be looking at these three technologies. If you look at the cost models, if you use the cost models I described earlier for anion exchange, and you punch in for nitrate, and the assumptions are on the green box to the right here for these costs, and the cost models will generate a total annual cost, and that's both capital and operation and maintenance costs blended together. And you'll get a cost curve that looks something like this. And it's over a range of design flows for a plant. So you can see how larger plants cost more than lower plants. Also shown here is in the cost models, we have a high cost category that we can click on and a low cost. So high cost would be using such things as lots of automation, using stainless steel piping instead of fiber, instead of PVC. And low cost would be choosing limited automation and using more cheaper products such as PVC piping. So this is the cost curve for nitrate. And if you can see, there's a little bit of a discontinuity right at 1 million gallons a day. And the reason for that is that small systems do have some cost savings. For instance, they can use prefabbed buildings. They can have sometimes residual handling flexibility in terms of maybe a septic system. They can have reduced spacing between vessels and smaller vessels and no redundant vessels, reduced instrumentation, no booster or backwash pumps. You know, they can have a thinner concrete pad thickness than larger plants, 6 inches versus 12, and they have reduced indirect costs. So that's why you can sometimes say, or you can save money with a small system. Now, this is the same assumptions here for nitrate control using point-of-use membranes. And it's the same total annual cost versus design flow. And the design flow only goes up to 1 million gallons a day because at about 1,000 households, that's where it gets very tricky to use point-of-use with over 1,000 households. So we limited this discussion to below 1,000 households. And at the very bottom end of the range is for a system that has only, say, 25 households. So that's the smallest type of situation you'll run into. And this is the cost curve. For this, you don't have the higher and low categories because they're just point-of-use devices that you can install. And here's the cost curve, the same cost curve for anaerobic biological treatment for the same assumptions. But you have additional assumptions in terms of post-treatment that needs to happen. You have to add in acetic acid and phosphoric acid into your biological system. And this is for a fluidized bed reactor. And you can run high and low costs in this case too. Now, if you combine all these 3 plots together, this is where it gets interesting. So this is for nitrate. They're all plotted together. So the red is the point-of-use membranes for 1 million gallons a day and lower. The anaerobic membranes or anaerobic biological fluidized bed is in green, and the anion resin is in blue. And you can see for very small systems that the point-of-use devices cost out as the cheapest option. And this is why sometimes they say point-of-use devices can be considered for very small systems and are cost-effective. And but then as the system size gets larger, that in this case, under these assumptions, the anion exchange resins become the least costly option from about, I don't know, 0.2 or 0.3 million gallons a day up to about 5 or 6. And then at that point, the biological treatment becomes fairly competitive with anion exchange. This kind of surprised us originally as we started crunching numbers for biological treatment because we kind of thought that biological treatment might be the lowest cost because it's biological. But this is not aerobic biological treatment where you add in some oxygen and you send it through a filter for, say, ammonia control. This is anaerobic, where you're getting rid of the oxygen and you're making it go anaerobic. And so the costs are higher and the complexity of running the system is higher too. Now, in different conditions or different assumptions, these curves will change somewhat, but I think this curve demonstrates how point-of-use devices can be a good option and something that you usually typically go to. Anion exchange resin is a fairly low-cost option for nitrate. Now, this is for fluidized bed reactor. If you looked at fixed bed system, that's shown in the green dashed line. For very small systems, you can see some cost saving for a fixed bed anaerobic reactor in this case, not so much for the larger small systems, but you do see some cost savings there. And so over time, you know, anaerobic biological treatment is a fairly new technology. Over time, those costs might be coming down. So we'll see what happens into the future. Now, this is for nitrate. If you want, we can do the same exact comparison or example for perchlorate. So this is at 20 milligrams of nitrogen per liter for nitrate. The next plot for perchlorate is the same exact axes, but at a much lower concentration for perchlorate. So this is perchlorate. And you can see how it's almost the exact same story here, except the influent is 24 micrograms per liter in this case, where we had some data from a full-scale system. So the perchlorate, in this case, again, you have the point-of-use devices being the least cost option, and then larger systems than, say, 0.1 million gallons a day in this case, upward, the anion exchange resins were the least cost option. Okay, so a little bit about cyanobacterial toxins. Cyanobacterial toxins can be in the cell or dissolved outside the cell. They're formed within the cell, and it's fairly easy to remove the cells as you're removing turbidity in your drinking water plant. You don't want to break the cells and release the toxins, because once they become dissolved, it's much more trickier to treat. So we're going to go into a little bit of those trade-offs. Here's a typical conventional plant. You can add powdered activated carbon up in your intake. You can add it in the rapid mix tank. You can add permanganate up front. Usually that's used for taste and odor control. Toward the end of the plant, you can add chlorine once you've clarified the water. And so here's a plot that demonstrates a few things. So if the toxin remains in the cell, most of the toxin then is removed before the filter. So chlorophyll A is plotted on the y-axis, and it's the green dots. And you can see that's representative of how many cells of algal cells are there, or cyanobacterial cells. The ELISA, or the toxin total, is in red, and the extracellular toxin is in blue. So all the toxin here is pretty much within the cell. And as you remove the chlorophyll, or the cells, you're removing the toxins. So by the time you get to the clarifier effluent or the filter effluent, your toxin levels are pretty much the lowest possible that they can be, along the lines of what's just in the extracellular. So in this case, the toxin remained in the cell and was removed very, very easily. Here's the effect of permanganate. So permanganate here, we've got a permanganate concentration in red. You've got the number of dead cells in blue. So as the permanganate reacts over time and drops, the number of dead cells increase in this reactor in blue. When you look at the toxin, what's happening is the permanganate is destroying the cells, and it's releasing the toxin into the water, the dissolved toxin, and then it's reacting with that toxin. So you can see the total toxins drop because the permanganate is reacting with it in the water in dissolved phase. But the extracellular toxin is increasing. So it's breaking it, dropping it into the solution, into dissolved state, extracellular, but then it's reacting with it. So in the end, you end up with almost all your toxin in extracellular form, but not all the toxin is destroyed by the perchlorate because it hasn't had enough time to react with it, or the perchlorate concentration wasn't high enough. So you have this trade-off with perchlorate that's happening. Here's another example of that. Perhaps it demonstrates it a little better. So the total toxin is in red, and the extracellular toxin is in blue. So the total toxin is fairly high, and it's all in within the cell, because the extracellular toxin in the raw water is 0. So as the post-permanganate, the extracellular toxin increases because it's released from the cell, but the total toxins are dropping because the permanganate is reacting with them. Post-powdered activated carbon, some of these extracellular toxins are being absorbed onto the PAC, so that drops, and you can see that into the total toxin too. After the filter influent, there's a little more time to react, and so these concentrations drop some more, and the water gets clarified, and the total toxin ultimately gets to a very low level, and then the chlorine hits in this case and results in a very low concentration in finished water. Here's a plot of CT, which is the concentration of chlorine versus the time of contact. And you want to have, this is a standard way of looking at the reaction for disinfection oftentimes, but it comes in handy this way too, because you want a high concentration of chlorine that reacts for a long period of time. This plot shows that at higher pHs, you're going to need a lot more chlorine or a lot more contact time to reduce the concentration, and in this case from 10 micrograms per liter to 1 microgram per liter of microcystin LR. So the story here is that at higher pHs, you'll need more chlorine and more contact time, likely due to the fact that it's in hypochlorite form. At hypochlorous acid forms down at pH 6, you need much less because it's more reactive. Also, at higher temperatures, you need less chlorine because the reaction rate is faster. And so the CT, you'll need less contact time because the reaction rates are faster at higher temperatures. So the bottom line to this plot is if you're dealing with a cold water and you're dealing with a high pH water, that's the maximum amount of chlorine or contact time that you'll need when you're dealing with a microcystin bloom. So a little bit about treatment options in totality between the different technologies. So powdered activated carbon removes some HAB toxins better than others. The carbon choice and choosing the correct dose are very important. Also, you'll have to look at reduced filter times and sludge disposal issues with PAC. For GAC, it also removes some toxins better than others. The removal depends on the amount of preloading that the column has seen before the toxin bloom. GAC has a high capital cost, and you'll have to look at reactivation and removal frequency for GAC if this is a bloom situation that is reoccurring. So that impacts your cost in operation. For UV technologies, for after treatment, once the water is clarified, it's probably likely not used for toxins because the doses that are needed for toxin removal are much higher than required for crypto or giardia or viruses. So it's unlikely a plant will have UV installed at the correct dose to remove HAB toxins. Permanganate, we discussed that a little bit earlier. So it can be applied earlier in the treatment processes while the concentration of the cells are still high. It has the potential to release toxins, but it also reacts with the toxins. So there's that trade-off that's going on. Chlorine, the degradation rate increases significantly with lower pH, and you need to balance other issues within your system. For ozone, it's a high capital cost, and if it's applied fairly early in the treatment, it has the potential for toxin release, much like permanganate. And chlorine dioxide is generally not considered effective against microcystin. So our last category of compounds to deal with for chemical of emerging concern are PFAS, or per and polyfluoroalkyl substances. They are a class of compounds. They're basically known because they have chlorine-fluorine bonds, which are very strong bonds, very stable bonds. And you can have these molecules in linear, branched forms. You can add in an oxygen, sulfur, hydrogen in various places and form different combinations. And these compounds are incredibly valuable to society in doing many different things. And so they're used very often. And this slide is just to show that there are whole classes of different PFAS, not just PFOA and PFOS, which we're more familiar with. And so there are thousands of these. Some of these are precursors to others. So if they degrade, some can degrade, but they degrade to other PFAS largely. And so it's a large assortment of PFAS. Just to note that the treatability database has a series of PFAS located within it if you go searching for it. So it has PFOA and PFOS, and then it has another category called PFAS, which includes data for some of the other more shorter chain PFAS. So what are the treatment technologies for PFAS? We do know that conventional treatment, low pressure membranes like ultrafiltration and microfiltration are not effective, along with biological treatment, which includes slow sand, disinfection, oxidation, even advanced oxidation. What is effective is anion exchange resins, and you get a very high % removal if designed correctly. High pressure membranes are very effective. Powdered activated carbon has a wide range of effectiveness, and that's due to carbon dose. Probably the best resource out there is Dudley et al., looking at different PFAS doses to remove PFAS. And if you're looking for a moderate amount of removal, PAC can do a good job. Say 50% removal is a reasonable dose of 16 milligrams per liter for an example out of Dudley et al. But if you're looking for 90% removal or greater, you're going to have to put in a lot of powdered activated carbon, greater than 50 milligrams per liter, which is very hard for a utility to do, both in terms of dosing and then handling sludge and other factors, and filter runtimes and such. Granular activated carbon can be very effective, but if you're using it in, say, a taste and odor removal, where the bud is online for 5 to 10 years, you're going to get very short, small % removals because the carbon's already exhausted with natural organic matter. But if you design it for PFAS removal, it's generally very effective. Now, this example is for PFOS. There are other PFAS that are out there, particularly the shorter chain compounds that have much lower capacities. And so their removals won't be quite as effective. But we can get into that in this next slide a little bit more and onwards. Here's another plot from the cost models looking at costs. But in this case, we're doing costs per 1,000 gallons of water treated. And the red line above is the cost for the removal of 1,1-DCA, which is dichloroethane. That contaminant is kind of on our verge of what we consider cost effective for GAC. So anything with a cost above that, we generally rule out pretty quickly. And you can see how in this case, PFOA and PFOS is going to be about the same, maybe even a little lower cost than PFOA. But PFOA is very similar to the cost of TCE. And so TCE, we know, is a compound that can be economically removed with GAC. And so we feel pretty comfortable about PFOA and PFOS in terms of the cost of carbon to remove those contaminants. However, as I mentioned before, there are a whole series of PFAS, particularly the shorter chain ones, that are less absorbable, even less absorbable than 1,1-DCA. So care must be brought to, if you're using GAC, knowing what PFAS you want to remove and knowing where your target goals are in terms of removal. And that's a very important issue to deal with for granular activated carbon. So a little bit, again, of just general comments about granular activated carbon. For PFAS, it's the most studied technology. It will remove 100% of the contaminant for a time. The previous % removals were just ballpark figures, but GAC will remove 100% of the contaminant for a time, and then it will start breaking through the column. And it has good capacity for some PFAS. Secondary effects for granular activated carbon are that they will remove a significant number of disinfection byproduct precursors. It'll help with maintaining disinfectant residuals. Will remove many co-contaminants such as pesticides, industrial contaminants, etc. And it will likely have a positive impact on corrosion. Anion exchange resins, like GAC, will remove 100% of the contaminants for a time, have high capacity for some PFAS, and because of the kinetics of removal and their capacity, much smaller beds are needed compared to GAC. Secondarily, it can also remove some co-contaminants, but we don't, for the selective anion exchange resins, that's a little bit more research needs to be done in that area. For high pressure membranes, and here we're talking about reverse osmosis or nanofiltration membranes, it has very high PFAS rejections largely across the board for PFAS. Of these technologies, this is the one that will take out the largest suite of PFAS, and it will remove many co-contaminants, and will help with a significant number of disinfection byproduct precursors. However, there are problems with help with maintaining disinfectant residuals for this. It will help with maintaining disinfectant residuals, excuse me. So, but issues to consider with GAC is that GAC runtime for short chain PFAS will be much shorter. So care must be taken in terms of knowing what you want to remove. Potential overshoot of poor absorbing PFAS will happen, where the strongly absorbing PFAS will chromatographically push the poor absorbing PFAS down the column, and you can actually get a higher concentration of the poor absorbing PFAS than what's in the effluent than what's going into the column for a time. Reactivation removal frequency needs to be addressed, and you need to look at disposal or reactivation of spent carbon. For anion exchange resins, the runtime for select PFAS is also shorter. You can also see this overshoot phenomenon with anion exchange resins if not designed properly. At this point, it has unclear secondary benefits. It probably removes a number of other contaminants, but we're not quite sure about that. And disposal of the resin ultimately has to be addressed. For high pressure membranes, it has very high capital and operating costs. However, membrane fouling, particularly for surface waters, is an issue. Corrosion control needs to be addressed at the plant. If you're using a point of use filter, it's not so much an issue because it can be handled within the unit itself. However, there can be some large issues if it's a point of entry device and you don't have any corrosion control dealing with or installed, because you can see corrosion in your premise plumbing if it's point of entry. And also, finally, perhaps the largest concern with high pressure membranes is currently there is no options or limited options for concentrate stream treatment or disposal. So what do you do with a fairly high flow rate of highly concentrated PFAS concentration stream? Where do you put that? How do you treat it? And those issues have yet to be fully addressed. So we're a little bit short on time, but this is the series of what EPA is working on. A lot of the issues I've discussed above previously for PFAS, looking really closely at variable influent PFAS concentrations, variable source waters, looking at reactivation of carbon and disposal options for both carbon and resins, and documenting secondary effects. So we're hoping we can be a value added with regard to choices toward PFAS removal for drinking water plants. When you have PFAS in your water, you have to do two things. One is eliminate the source of PFAS, and the second is to choose either a new source of water or a technology design or operational scheme that will reduce the PFAS. And so a lot of the issues I discussed previously about having to have the cost being affordable, making sure your staff can handle the operational scheme over the long term, that the technology can operate long term under a reasonable maintenance program, and that technology and treatment train can handle source water changes, and any waste stream generated can be treated or disposed of in a cost-effective and sustainable manner. So we all know situations where you change a source water or impact the technology, and sometimes it has a negative impact on both treatment and distribution. But it's also the case that technologies can have positive impacts on your treatment system. So you can have improved control of pathogens, better control of taste and odor compounds, industrial contaminants, pesticides, pharmaceuticals, personal care products, etc. And also it can have positive impacts on the distribution system for lead and copper, corrosion, disinfection residual maintenance, fewer disinfection byproducts. So it's so in that regard, it's the goal of PFAS treatment. And in this day and age where each state is starting to set regulations for PFAS, utilities are wondering where it's going. But with regard to PFAS control, it's very important to look holistically and in terms of what your treatment technology can do across the board, and not just for one contaminant at this time. So, and that finishes my talk. So I think I'm ready to pass the podium.
Thanks, Tom. Okay, just a few things. We're going to go ahead and set up the poll questions now. So we'll put that up here, and you can answer. You'll have just a few seconds here, really, to answer each question. So just do your best. And while you're doing that, just a reminder that if you have people in the room with you, if you could type that number in the questions box, that really helps us out with our outreach efforts. And also, if the people in the room with you would like a certificate, go ahead and type their name in the questions box as well, and we'll make sure they get their certificate. And again, throughout, like a lot of you have been doing already throughout the talk, in the next talk coming up, if you have any questions for the presenters, just type them in the questions box, and we'll get to those during the Q&A session here after the next talk. Oh, I believe we are on our last question here. I'll give you guys time to respond to that. All right. And we'll go ahead, while you're answering the last one, just a reminder again to about the certificates, being certificates of attendance. And again, we will, if you type the names of the people in the box who are in the room with you, we will actually send those to your email unless you specify otherwise. So we'll make sure everyone gets those certificates at that email. Okay, and with that, while you're answering the last question, we're going to go ahead and move to our next presenter. And while he's getting his slides set up, the next presentation is from Brian Bernadotte. He is with California EPA's State Water Resources Control Board and their Division of Drinking Water, where he's worked for the past 26 years. Brian will be talking about treatment approaches for 1,4-dioxane in reuse and in groundwater. Hey, Brian, you can take over.
Okay, thank you. Good afternoon to most of you. It's still a little late morning in California where I am. And I just want to say a little thanks to EPA. I know as a state regulator, and a lot of you probably are regulators, EPA is a great resource. And so I want to thank all the people at EPA. They're very helpful. Advance this. Okay, there we are. So wanted to acknowledge these people, especially my boss, but also our chief in the LA region and the EPA website and a couple of cities that are dealing with 1,4-dioxane. And if you go to the website, the EPA website with their fact sheet, just briefly, 1,4-dioxane is a synthetic industrial chemical completely miscible in water. It is likely a contaminant at many sites contaminated with certain chlorinated solvents, particularly 1,1-trichloroethylene. It's widely used as a stabilizer for chlorinated solvents. So that's on the EPA website. Just this morning, I was playing around and I looked at the Environmental Working Group's website, and it's also in a lot of personal care products. So, for instance, one of the top ones on their site is Banana Boat sunscreen. So, and then there's a whole list of a lot of personal care products. So, I think that's kind of interesting. Now in California, we do have a lot of contaminated groundwater, and so this is roughly what is in California. And many are standby inactive wells, so they're kind of just sitting there. Very few are treated, but there are some that have advanced treatment, so I'm going to go into that. Now in California, it's considered an unregulated contaminant, but we have something in California called a notification level, which our state legislators thought it was a good idea that if it's over this notification level, then the public water system must notify the public of that. So the NL for 1,4-dioxane is 1 microgram per liter. And the EPA risk assessments indicate that a 10-to-1 cancer risk assessment would be 0.35. Now, again, it's in wastewater and groundwater, and it's difficult to remove due to the low octanol water partition coefficient. Again, it's common in water, and basically the treatment technology is advanced oxidation. So that's my focus today, is advanced oxidation processes, or AOP. Now, in the ground, there is bioremediation, and I'm not going to cover that. In California, there are a number of cleanup sites in Southern California that, are the responsible party has put in treatment. And the question has come to our state regulators, can we send that treated water to consumers? So to do that, we require advanced oxidation for that groundwater. Now, potable water via groundwater recharge, I'm going to talk about, because that's happening in California and other places in the country, and it's one of the future emerging technologies. Now, it's been done in California for over 50 years, but it wasn't until the 1990s that we realized 1,4-dioxane was detected, and we had early draft groundwater recharge regulations that failed to address 1,4-dioxane. So it was found in wells, and it wasn't regulated, as I mentioned, but we knew it was a potential health concern. Fortunately, the people that detected, so in Orange County, that's where it was first detected in the late 90s, they rapidly put in treatment, and it was very effective in response to that. So full advanced treatment is a terminology in our regs in California, required for groundwater injection and surface water augmentation projects. So that involves a combination of reverse osmosis followed by advanced oxidation. Now that addresses nitrosamines like NDMA and 1,4-dioxane, but it also addresses a lot of other unknown constituents of emerging concern like pharmaceuticals and personal care products. So reverse osmosis in general, as we know, are very effective for most organics. It's large organics. RO is less effective at removal of small non-ionic neutral compounds, such as 1,4-dioxane, which has a molecular weight of only 88. So therefore, our regulation requires that these recharge projects meet the notification level of 1, and that includes advanced oxidation. So it's a combination of high-dose UV, and UV by itself will break down the NDMA at high doses, but it cannot metallicize 1,4-dioxane very effectively. So advanced oxidation is added, and most experts in potable reuse agree 1,4-dioxane is an appropriate indicator for a lot of other organics. So an indicator is a kind of a sentinel chemical that if you're removing that, you think you're removing a lot of other chemicals like it. So the addition of peroxide creates hydroxyl radicals to reduce the 1,4-dioxane and other organics. Now, this has been utilized at Orange County Water District seedwater intrusion barrier for over a decade. A new kind of modification is switching from peroxide to free chlorine to create both chloride radicals and hydroxyl radicals. Now, the advantage of that is operators can measure free ammonia and free chlorine residuals. So to produce radicals, you need UV at very high energy levels, higher than needed for most disinfection. So, if you look at the long-term 2 EPA tables, you go from a dose of around 11 to 186 millijoules per centimeter squared to inactivate microorganisms. 11 is for 3 log Giardia, 12 for 3 log Clostridium, 100 is for most enteroviruses in wastewater, 186 is for 4 log adenovirus. Now, most reuse projects in California add peroxide to create hydroxyl radicals to meet the requirement of at least a half log reduction of 1,4-dioxane in a regulation. Now, it's difficult to quantify hydroxyl radicals because they're very reactive and short-lived. So basically, you're just relying on high energy and adding a certain amount of peroxide. And Orange County just stays steady at 3 parts per million peroxide added. Now, our regulation requires that the proponent show that the AOP will provide that half log or 69% reduction. So that they go through demonstration testing to show that. And parameters that can be monitored online are, of course, UV dose and also UV transmittance. These can be monitored continuously. So now I want to move to drinking water, specifically groundwater. And I'm going to borrow from a talk given last year at the 2018 International UV Association Conference. What I'm showing here is what's being built in by the City of Los Angeles Department of Water and Power in the North Hollywood area of their service. And of course, the upstream of the AOP, there's, typically a lot of the large systems put in sand separators and cartridge filters because you don't want the UV sleeves to be broken. That would be kind of a disaster. So you wouldn't want that to happen. So that's kind of an insurance policy. Now I'm showing this relative effectiveness of a balance between the amount of peroxide added and the amount of dose, basically energy. So as you can see, you need a lot of high energy to get anywhere for 1,4-dioxane, and you can use a lower dose if you add more peroxide. So there's a balance there. So you might, depending on the cost of energy or peroxide, try to figure out what the best mix is. And just to point out, some of the plumes in California could have very high levels of organics. So you may need up to more than 1 log removal. So it just depends on how contaminated that area, that well is. Now, just a word of caution. Personally, the graph that I previously showed is an approximation. I wouldn't use it for design. It was based basically on bench scale tests, and my experience with UV at bench scale, especially advanced oxidation, is that it's probably very conservative, but it's probably over on the high side. And the actual dose is highly dependent on water quality. As with all UV, the transmittance is very critical. And fortunately, the transmittance is typically high in groundwater and in RO permeate, so it works for our potable reuse. Now, there's certain water quality parameters that impact the amount of scavenging. So there's this new term you may not be aware of, hydroxyl scavenger demand. Sort of like oxygen demand, but this is hydroxyl scavenger. And these type of things are things that could affect the effectiveness. So these will actually, instead of the hydroxyl radicals reacting with the chemical you're trying to degrade, it'll be absorbed by these other parameters. And so you want to get a good idea of your groundwater. What usually you can control the amount of chloramine, but the amount of TOC or nitrite, not nitrate, bromide, and especially alkalinity seems to have a big impact on effectiveness because it's a high scavenger. So here's a picture of an inspection I did a year ago in Monterey Park, which is in LA County, just east of LA. And I'm going to quote from their website. They say Monterey Park pumps from the San Gabriel Basin, which contains contamination from irresponsible groundwater disposal dating back to World War II. So here's something that happened 75 years ago, and now we're dealing with it. So in this case, there's 3 wells, all with different levels of 1,4-dioxane. And so in this type of situation, you blend before you treat it, but you want to make sure you can address one well if that's the only one it's on. So you have to design for the highest concentration. Typically. And so this is basically historically high concentration. And as you can see, they had a whole mixture of things. And I didn't pick all of them, but these are the ones I think are the most significant. And in their case, 1,4-dioxane, certainly they want to remove that, but the tetrachloroethylene, or PCE, is really the main concern. And so in this case, they designed the advanced oxidation for a 3-log reduction of POC. They were trying to be very conservative and go to like a non-detect level, lower than our NL of 1. But anyway, so the design is conservative. Now, in this case, we had results from their demonstration study that showed that the hydroxyl scavenger demand varied over time. And so after we got these results, we realized that what they thought, we had them run at certain flows and certain, power and things like that, just to see if it was working as was predicted. And actually, it underperformed. And the reason given by the manufacturer, which I understand the technology, is that the alkalinity changed. It went up over 6 months, and the scavenging demand then basically impacted it. So what we're going to make them do, because this is about ready to go online, is to do regular monitoring of scavenger demand so that they can accurately predict the removal. Now, just more on these 2 sites. It's effective, as I mentioned, for a lot of other volatile organics, like TCE, PCE, or 1,1-BCE. Now, the peroxide doses in groundwater are much higher, as you probably could see, than polar reuse. So greater than 10 milligrams per liter at these groundwater sites versus the 3 milligrams per liter at Orange County Water District seawater barrier. And because of that, there's going to be a lot of peroxide that is not converted to hydroxyl radicals. So you're going to need post-treatment to quench the excess peroxide. So that's why, in this case, they have a lead lag GAC after the UVAOP for both sites. And then just quickly, I want to mention, because I think there is some international interest in this, I've been part of a group over the last 2 or 3 years that was basically started by the local Cal Nevada American Water Works, but in conjunction with the wastewater side, because we realized that these advanced treatments, you're kind of getting to a place where both need better trained operators. And so we assembled 30 to 40 diverse members, operators, utility people, regulators, to come up with a plan to adopt the certification just for advanced treatment. So as you probably know, it's advanced things like RO and UV are normally not covered in the normal state certification testing. So we realized there was a gap there and we needed to do something. So I would encourage you to go to this website. This exam is going to be available in spring, specifically for California, but I think they'll open it up to anybody that wants to take it as an option. I think that's what they're going to do. So I just wanted to mention that this has been a gap that we regulators have been wanting for a long time. So in summary, AOP is effective for reduction of 1,4-dioxane, but also for other VOCs as well. Hydroxyl scavenger demand can be an issue. So strongly recommend collecting existing water quality parameters and repeat them often. And just in general, I always recommend this as a regulator. It's not necessarily required, but it's highly recommended that pilot testing occur. And I think it's especially important for this advanced technology. But even the technologies that Tom was talking about, we recommend it even for POUs because there are issues that come up in water quality parameters that are unforeseen. And so as we're implementing it in California, we do recommend pilot testing even for the POUs.